So let's talk about some examples of algebraic groups quickly. So we've already seen the algebraic group G is GLN of K. For this, the coordinate algebra is the polynomial algebra in n squared indeterminates. These are the ij coordinate functions of n by n matrices, and then you have to localize at determinant, so you have to invert determinant. And let me see, what else did we see about this? We could talk about the co-multiplication m star from k of g to k of g tensor k of g. And that's because that's an algebra homomorphism. It's actually uniquely determined by where it sends the j's to these coefficient functions. And it's not very hard to see because this is just dual to the matrix multiplication formula that this co-multiplication m star sends tij to the sum of the tik tensor tkj's. The co-unit, that's evaluation at the identity, that just takes tij to the Kronecker delta, because the identity matrix has a 1 on the diagonal and zeros off the diagonal. That's the co-unit of the Hopf algebra structure. And let me see the antipode. That's the one I always try not to write down. So remember, we had I was the group inversion, and then the comorphism of the group inversion operation, that's the antipode. And if you wanted to calculate that, you would need to know what it does to tij, and that's that nasty formula. For the ij entry of the inverse of an n by n matrix. If you write that in terms of the tij's and 1 over determinant, that'll be the image of this tij under this antipode. So it's quite explicit. You see exactly this coordinate algebra in this case, and you can explicitly see what the Hopf algebra structure looks like. Okay, so that's one example. Another example I guess we should mention is that any finite group is an algebraic group. That's sort of a triviality. Any finite set is an affine variety. Any function between finite sets is a morphism of affine varieties for kind of trivial reasons. More interesting maybe is the observation that any closed subgroup of GLN of K, or indeed any closed subgroup of any algebraic group, is again an algebraic group. Because it's a closed subset of an affine variety, so it's an affine variety, and it's a group. And since the group operations are just the restrictions of the one upstairs in the big group, those are morphisms of varieties. So that's a great source of new algebraic groups by taking closed subgroups of old ones. In fact, later today I'm going to show that the converse of this statement is true, so that any algebraic group is isomorphic to a closed subgroup of GLN of K for some n. So really, this is kind of the master example. All algebraic groups arise in this way. But let's just write down a few kind of fairly simple examples of closed subgroups of GLN of K. For example, there's SLN of K. So that's all G in GLN of K of determinant 1. So the vanishing ideal here is going to be generated by the single function determinant minus 1 in the coordinate algebra of GLN. Okay, so in fact that'll generate a radical ideal, and That's exactly the ideal that cuts out SLN of K as a closed subgroup of GLN of K. Okay, so SLN, that's another algebraic group. What else can I think of? What about the group I call BN of K? So this is the group of all elements of GLN of K such that the ij entry of G is 0 for I bigger than J. So the ideal, defining that, that's the TIJs for I bigger than J. They generate the radical ideal that's the ideal for that closed subgroup Bn of K of GL and N of K. So of course this is upper triangular invertible matrices. Another simple example is Tn of K. So this is all the G in GLN of K such that Gij is 0 for I not equal to J. So this is very similar. This vanishing ideal is generated by the coordinate functions for I not equal to J. So this is the diagonal invertible matrices. So none of these are super important, super exciting examples, but they're important ones. One more along these lines is UN of K. So U here is U for unipotent. So this is the group of these upper triangular matrices with ones on the diagonal. I use the kind of funny word uni-triangular. So that's actually a normal subgroup of Bn of K. And you can convince yourself that the quotient of Bn of K by Un of K is actually isomorphic to Tn of K. So this is a closed subgroup of GLN. Again, in fact, it's a closed subgroup of Bn, and the vanishing ideal for this would be generated by all the Tijs with, let's see, how do I write that? The Tijs with I bigger than J, because that was what generated the vanishing ideal of B. And then you also need to force the diagonal to be 1. So let's see, maybe I should write TKK. So that those will be the polynomials cutting out Un of K as a closed subgroup of GLN of K. It's the vanishing set of those polynomials that I just wrote down. Okay, so those are simple enough examples. We could work out their dimensions, actually. They're all irreducible. Remember that GLN of K has dimension n squared. SLN of K is going to actually be of dimension just n squared minus 1. The determinant is 1, so we're just cutting out a hypersurface inside n by n matrices. And let's see, what else did I have there? I had Bn of K, upper triangular matrices, that's going to have dimension half n plus 1. Tn of K will have dimension n, and Un of K will have dimension half n minus 1. Those are all just pretty common sense things. You can just visibly see the number of parameters in each of those groups, which gives this dimension in these easy examples. Okay, I'm just trying to write a list of a whole bunch of examples, so maybe the next one's I'm not going to prove this, but you can think about it. Any centralizer or any normalizer of any closed subset of an algebraic group. G is a closed subgroup. Okay, so the sort of centralizers and normalizers, the things you normally play with when doing basic group theory, providing you start with a closed subset, those give you new algebraic groups because they're closed inside the original group G. I wanted to also mention just a few things just briefly next about the classical groups. So this is another very important family of linear groups, of algebraic groups. So let me see. to set these up kind of fairly swiftly, let's just work in coordinates. So let's take a non-degenerate, either symmetric or skew-symmetric bilinear form on, so I'm just gonna take this on the standard vector space of column vectors, so I'm in coordinates already, and so there we go. In the skew-symmetric case, the existence of a non-degenerate skew-symmetric form implies actually that this n has to be even, so you can write n is 2m, so that it's even. Let's let J, capital J be the n by n matrix with ij entry just jij there. So this is I usually use J for the gram matrix of this form. So this Jij is just the inner product Vi Vj for the form where here V1 up to Vn is the standard basis. We're in coordinates, so we're in Kn, we've got a standard basis around. And then the group G that I'm interested in, it's going to be all matrices, all automorphisms of the vector space V, this Kn, which preserve this bilinear form. So here's the way you would write it if you were coordinate free. But we're in coordinates, so you can simply translate this very quickly into an equation involving this gram matrix. And so here it is. In fact, this is a single matrix equation. So the entries of that matrix equation give you n squared equations, and it's easy to see that each of those equations is just a quadratic equation in the entries of the matrix G. So it's a kind of polynomial equation, and so it's cutting out this as a closed subgroup. Hence, an algebraic group in its own right. So there's kind of two cases here. In the symmetric case, this G is the orthogonal group. I guess you normally take J, if you were doing that, like most normal people would take they would pick their basis so that gram matrix was just the identity matrix. And so this equation is just G transpose G is the identity. But I'm not quite a normal person. I prefer to pick my basis so that the gram matrix is this kind of not identity matrix with the ones down that skew diagonal. So we're looking at matrices with this property. So this is kind of a better choice for our canonical gram matrix in the orthogonal case. And I'm not going to explain why that's a better choice. Since we're over an algebraically closed field, all non-degenerate symmetric bilinear forms are equivalent up to change of basis, right? So normally you would pick the basis so that the gram matrix was just the identity matrix, and then you had an orthonormal basis. But I'm weirdly going to pick my basis so that this is my preferred choice of gram matrix, and I'm going to call this the orthogonal group On of K in coordinates. So I'm going to use this skew diagonal Gram matrix when I talk about the orthogonal group. I know that's unconventional. Normally you would pick that equation, but I'm picking that one. So that's the symmetric case, and then in the skew symmetric case, so here in the skew symmetric case, G is called the symplectic group, and so again, there's kind of two choices. I think many people would so again, up to change of basis, there's only one non-degenerate skew-symmetric bilinear form on this 2m dimensional vector space, and many people would pick their Gram matrix so that it was these little 2 by 2 blocks, 0, 1, minus 1, 0, 0, 1, minus 1, 0, 0, 1, minus 1, 0. But I think it's much better to pick this one, where you have the identity, the skew identity in that corner, and it's minus in that corner. And so from this one, I'll call G the symplectic group SP2M of K to be the one where I pick that particular Gram matrix. So I'm kind of going very quickly through this stuff because there's some stuff about these two groups, ON of K, the orthogonal group, and SP2M of K, the symplectic group, on the first homework sheet. So I'm not going to kind of go into this in any detail at all right now, but just to make sure that you take a look at that. If you have an element of the orthogonal group, its determinant is either plus or minus 1. And so you kind of quite quickly see that there's a short exact sequence where this last map is the determinant map going on to plus or minus 1. And I shouldn't write 0 because it's a short exact sequence of groups, so this is the trivial group. And in here, so this is the kernel of determinant, and it's called the special orthogonal group. So that's kind of a little bit curious for the orthogonal group that in fact the orthogonal group has these two different connected components. There's the component of determinant plus 1 and the component of determinant minus 1. And so that plus 1 component, that's actually a normal subgroup of the orthogonal group of index 2 called the special orthogonal group. This is all assuming you're not in characteristic 2. Characteristic 2 is a little bit exceptional for orthogonal groups, and I'm just not going to worry about it. I'm going to assume you're not in characteristic 2, because remember, very soon we're going to be over the complex numbers. But this extra little complication does not happen for the symplectic group. If you have G in the symplectic group, it's automatic that the determinant of G is plus 1. So in fact, SP2M of K is and the special orthogonal group too. But in the orthogonal case, I had to take determinant 1 as well as an extra condition. These are actually both connected. But it's actually equivalent for algebraic groups to being irreducible varieties. This is something we're going to talk about a little bit next time. But since I'm talking about these classical groups right now, it's worth mentioning this. So there's SP and there's SO. They are both connected algebraic groups. So those are going to be super important when we get into the world of Lie algebras. We'll understand things much better at that point. But being as SP and SO are both irreducible varieties, it's totally reasonable right away to ask, well, what are their dimensions then? And already that gets you into a question, although we know explicitly the equations that cut these out as closed subgroups of the general linear group, from those equations to work out actually what are the dimensions of these affine varieties isn't immediate, and we'll need to think about that a little bit more as we get a little bit more machinery in front of us. So I guess right now this is a hard question to answer. Okay, so that's done just a bunch of examples fairly quickly. That's all I wanted to do in that part of today's lecture. The other thing I want to do is I want to prove Cayley's theorem for algebraic groups, which I also mentioned briefly earlier. So this is the following theorem. Every algebraic group G is isomorphic. Well, in short, every algebraic group G is linear, by which I mean it is isomorphic to a closed subgroup of the general linear group for some n. So it's the analog of Cayley's theorem from finite group theory, where you would have the symmetric group Sn appearing in that case. So let's see. I want to try and prove this. I've got roughly half an hour. I think that's just enough time to try and prove the theorem. So I haven't maybe used the word isomorphism, but of course I've defined morphism for algebraic groups, and isomorphism is a morphism whose inverse, an isomorphism of algebraic groups is a morphism of algebraic groups whose inverse is also a morphism of algebraic groups. So there's a little bit of a subtlety here, which it doesn't happen in abstract group theory, but it definitely happens in algebraic geometry. Even for affine varieties, it's perfectly reasonable to have a morphism of affine varieties that is bijective, so it's invertible as a function, but whose inverse is not a morphism of affine varieties. So to check that you've got an isomorphism of affine varieties, it's actually not enough to check that it's a morphism and that it's a bijection. And the same carries over to the world of algebraic groups, although it's not quite so easy to find an example of two algebraic groups which are isomorphic as abstract groups, but not isomorphic as algebraic groups. I would give you examples, but I would want to work over a field of positive characteristic before I could give them, and these kind of somewhat pathological examples usually involve some sort of Frobenius morphism arising in positive characteristic. So I'm not going to write any of that discussion down. I'm just going to write the word careful under isomorphic. You really have to check that there's a two-sided inverse, which is also a morphism of varieties. Okay, so let's see if we can prove the theorem. I think in my proof I'm going to need a little lemma at some point, which I guess we could have noted long ago. And it's kind of it's quite useful. So let's maybe just write this down properly. This little lemma. So let me see. It's kind of one of those silly lemmas that you suddenly stumble into needing when you're not paying attention. So X here is an affine variety, and I've got A1 up to AM in the coordinate algebra, which are linearly independent. And then the lemma says that there exists points x1 up to xm in X, such that the matrix AI of xj for 1 less than equal to ijm. So this is just a matrix of scalars in the ground field. There exists at some m points, so that this is an invertible matrix. So I've just written the lemma down. Let me prove the lemma. It's not very difficult at all. but I'm going to write the proof down, then I'm going to erase it so that we just have a little record of that lemma in the corner of the page there. The proof of the lemma is kind of fairly straightforward. You look at the sum over the symmetric group Sm, sine of that permutation, a pi of 1 tensored a pi of 2 all the way up to a pi of m. So that's in the tensor product of m copies of the coordinate algebra of x, but that's the same thing as the coordinate algebra of the Cartesian product of m copies of x. And this is non-zero because, well, we're just in this tensor product, and each of these AIs were linearly independent in the first place. So it's completely immediate that this linear combination of tensors is not the zero element in this tensor product. And so since it's non-zero, there exists a point, x1 up to xm, in x cross m. So this function is not zero at this point. So this is, I guess this is really the Nahl-Schlellensatz is in the background here. So if you've got a non-zero function, that means you could find a point on which it's not zero. That's not the Nahl-Schlellensatz or anything. That's just what it's because this is an algebra of functions on this set. So being the non-zero function means that there's a point on which it's not zero, and then when you evaluate, this gives you exactly the determinant. So when you evaluate this function on this point, it's not zero. That's exactly that evaluation is exactly that determinant. So that determinant of that matrix is non-zero, so it's an invertible matrix. Okay, so not very elegant or pretty, but an often useful little observation. If you have linearly independent functions on your variety, you can find some points in that variety so that matrix of scalars is an invertible matrix. So I think I'm going to need that in just a second. But I don't want to leave that proof there because I'm not very proud of it. There we go. Okay, so now we're in business. Let's see if we can now prove Cayley's theorem. So what we're given an algebraic group G, and our goal is to find some n and some closed subgroup of that GLN, and such that that's isomorphic to the G. So to do this, we need some n-dimensional vector space. We need a finite dimensional vector space V on which G acts. So we have to somehow find some source of finite dimensional vector spaces which G leaves invariant. And where should we look? Well, we should look in the coordinate algebra. So if you have any element little g in G, there's a linear map I'm going to call rho sub G from the coordinate algebra of G to the coordinate algebra of G. I'll call this right translation by G. So this is just sending function f in the coordinate algebra to rho G of f, the right translation of f by G, where rho G f is the function whose value on some other h is f of hg. And you see why it's called right translation, because I multiplied on the right by G. And so from this you get this thing called rho, from G to the general linear group of automorphisms of the vector space K of G. So this is this group homomorphism. So this is this right regular representation of G. So a little bit of care is needed here. You see, I've written GL of K of G. I just want to observe that this is not in general an algebraic group, because this coordinate algebra is usually an infinite dimensional vector space. So I'm just thinking about this as just being some abstract group, the group of invertible linear maps from the vector space K of G to itself. But this row here, sending element little g in our group to this linear map rho sub g, this is for sure a group homomorphism. So that's a great big vector space on which G acts, but we need a finite dimensional vector space in order to prove this theorem. Fantastic. Okay, so let's see what we can do with this. I need one little claim, which is that any finite dimensional subspace W of K of G is contained in a finite dimensional subspace V of K of G, which is invariant. Under rho G, under right translation, by every G in G. So we've got to prove that claim before we do too much more. Well, it suffices to do this in the special case that this subspace W is actually just one-dimensional, spanned by some non-zero function f. And in that case, what I'm going to do is I'm going to just define V to be simply the span of all the translates, all the right translates of f for all G in G. So this is obviously invariant under right translation. And what I have to do is show that this V is actually finite dimensional. And to do this, all you have to do is you look at the co-multiplication M star. So this is this algebra homomorphism from K of G to K of G tensor K of G. And I'm going to assume that M star of F is, well, it's something in K of G tensor K of G, right? So you can write it as a sum of tensors for some n here. Okay, so yeah, that's just, it's an element of that tensor product, so it's some finite sum of tensors for some fi and fi prime in K of G. Let's just think about what happens if I take an element of the group, little g, and right translate my f. So to understand that, I have to apply that function to some h, so that's f of hg by the definition of right translation. But you see here, this is f applied to a product, so I can just as well calculate that by co-multiplying f and applying that to the pair h comma g, which is, what is that? That's fi of h, fi prime of g. And so this implies that actually rho g of f is just the sum of the scalars fi prime of g, fi, I goes from 1 to n, because both that function and that function take the same value on every h. So those are equal functions. So this is a very useful formula. So this is how I do the right translation of f. Rho g of f is just this linear combination of fi's. And so you see what it does is it shows that this right translation of f lies in the span of f1 up to fn. But this has got nothing to do with this has got nothing to do with g. It only depends on f. because we just used m star of f to calculate this thing. And so this shows that our v, the span of all of those right translates the rho g of f's for all g, shows that v lies in this span of these vectors. And so the dimension of v is actually less than or equal to n. And that does the job. I've proved that v is finite dimensional. Okay, so that's proving my claim. So now, given the claim, I'm now going to pick f1 up to fn in k of g so that they're linearly independent and so that they are algebra generators for this algebra k of g. If I apply the claim to the space W spanned by those guys, I may have to make this vector space a bit bigger. I get this finite dimensional vector space V containing W, which is invariant under all right translations. So I might have to do that. This vector space might get bigger, and then I'll pick a new basis for that V, and I'll get maybe a slightly larger set of linearly independent algebra generators for K of G, and I'll just replace. So applying that claim to this W, you make a little reduction. You may assume that V is the span of f1 up to fn is invariant under all rho g's, and that these f1 up to fn are linearly independent algebra generators for our coordinate algebra. Okay, so that claim is how I concoct this finite dimensional vector space, and then I'm going to look at this homomorphism from G to GLV, sending G to this right translation restricted down to V. This then is a group homomorphism. And this is going to be, if this V is of dimension n, this is going to be how I'm going to realize G inside some GLN. It's going to be the n that is the dimension of this V. Okay, so now the next claim, we're kind of very close here, is that the co-multiplication on this subspace V of K of G that I've constructed in this way actually lies in V tensor K of G. And so to prove this is where I need my little blue lemma that I gave you a few minutes ago. So I have to take any f in V, and you look at the co-multiplication of f. So it's going to be some linear combination AI tensor BI, where you can choose this so that these BIs are linearly independent. So this is for AI and BI in K of G. Now, as in the previous claim, it's easy enough, you just repeat what we did earlier to see that this right translation of f by some element of G is equal to the sum of the BI of G AIs. That nothing's different there. And now apply that blue lemma to get some points G1 up to Gm in G. So this matrix BI of Gj is an invertible matrix. Okay, so now what you have to do is now you look at these rho Gj Fs. So by our formula, This is exactly the entries of this invertible matrix applied to GI. So a linear, let me give myself a little bit more room. So this is kind of one of those long and tedious arguments. A linear combination of these, because this coefficient matrix here is an invertible matrix, you can look at all of these functions as j goes from 1 to m, and you can take a linear combination of these gives ai. But each of these guys is a right translate of f, and f was in v. V was stable under right translation. So a linear combination of these guys, it's certainly in v, and because this coefficient matrix is invertible, that shows that ai is in v for all I is 1 up to m. So this proves the claim. What I've just done is I've shown that for any f in v, m star of f can be written as a linear combination ai bi's, and all these ai's are in v. So this is something in right here in v tensor k of g, which is exactly what's needed for my claim. So we're really just about there. I can finally fit this together by the claim. In fact, if I try and calculate the co-multiplication on one of our basis vectors, remember v was generated by f1 up to fn, that was a linearly independent basis for v. This co-multiplication on fj, this is something in v, so the co-multiplication sends v into v tensor k of g, but the fi's give a basis for v, so we can write it like this for some fij in k of g. Now I'm going to look at this homomorphism from phi from g to glv that I talked about earlier, sending g to this right translation restricted to v. So this is a group homomorphism. But I've got my basis f1 through fn picked for my v, right? So this is actually just gln of k via that basis. And if you write that right translation as an n by n matrix in that basis, you find that it's exactly fij of g is that n by n matrix. So these fij's, they're exactly the entries of that of the matrix representation that we've got in this way. So this shows that phi star, the comorphism of this morphism, so phi star goes from the coordinate algebra of this gln of k to k of g, takes tij, the standard matrix coefficient function in the coordinate ring of gln, exactly to this fij, which is in the coordinate algebra of g, i.e. that phi is a morphism of varieties. So here we have a group homomorphism and a morphism of varieties. In fact, phi star is surjective, as the fij's generate the coordinate algebra of g. How do you see this? Well, let me see. From this identity right here, if I evaluate at, you see I'm going to evaluate at e comma 1, and you get then that I'm trying to do this correctly. what do I need to do here? I want, okay, I'm going to evaluate at E, comma, G to get, okay, that looks right. So if I take this identity and I evaluate both sides on the point E, comma, G in G cross G, so the left-hand side, because there's an M star there, that's the same as Fj of G, and the right-hand side gives me the sum I equals 1 to n, Fi of E. Oh, I did the wrong one. That's good. No, Fi of E, Fij of G, which tells us, since this is true for every G, this tells us that Fj is the sum Fi of E, Fij. So why do the Fij's generate their coordinate algebra? Well, this follows as Fj is in the span of the Fij's by this equation that I just derived there. And the Fj's generate K of G by their original choice. So now what I've just shown, I think this actually finishes the proof, because I've got this morphism phi of algebraic groups. Oh, I'm trying to write this in black. There we go. And the fact that the comorphism is surjective shows that phi is a closed immersion. So it's actually an isomorphism between G and its image, which is a closed subgroup of this GLN of K, this GLV here. And that was a somewhat hasty proof. It's quite a long argument, so I kind of tried to go through lots of steps as quickly as I possibly could to squeeze it in here. That's the proof of the analogue of Cayley's theorem for algebraic groups. So every algebraic group is isomorphic to a closed subgroup of some finite general linear group.